Hello everyone, welcome back to my channel Deep Understanding of Research Papers. Today I am going to cover a new tutorial of the paper X-Vector Robust Embeddings for Speaker Recognition. A person named Joshua Liu requested me in YouTube to create a tutorial of this particular paper, this X-Vector paper. So I am doing this tutorial, and this paper is by David Snyder, Garcia-Romero, Gregory Sell, Povey, and Sanjeev Khudanpur from Johns Hopkins University. And in this paper, in this tutorial, we are going to cover the overview first, overview of the paper, like what does this X-Vector mean and what are these speaker recognition systems are doing. Then we'll see the different speaker recognition systems actually, like which were developed over the last years, and these systems, the new systems, the old systems act as a baseline, and we compare this new X-Vector system with the previous state-of-the-art speaker recognition systems. Then we'll see the experimental setup, and finally we'll see the results where we see how much improvement we get using this X-Vector system. So in the overview, as I said, this paper is basically speaker recognition system. So when we say X-Vector, so you can use X-Vector is sort of, I'll tell you why this is called X-Vector. It's a sort of embedding, the name comes because of some embeddings. I'll explain you that. And this is basically a speaker recognition system. And this paper is nothing much different compared to one of the paper which I have recorded before. It's called Deep Neural Network Embeddings for Speaker Recognition by the same authors, where they showed how to use time delay neural network, also known as DNN, to do speaker verification or speaker recognition, and they get a huge improvement. And that paper I already recorded. It's already in my YouTube channel. If you want, you can go back and listen to that. It has much more detailed architecture review of what is exactly happening in that paper. And this paper is sort of extension of that paper, where they add some sort of augmentation to that particular same experiment, and they get some more results. So that is this X-Vector system basically. So we'll see what are the actual differences between that old deep neural network embedding with for speaker recognition paper with this new X-Vector paper. And as I said, it's a sort of the old idea itself. It's a TDNN based deep neural network itself, but TDNN based speaker recognition system itself, but it has this data augmentation technique. I'll explain this, what is this data augmentation and how they are doing this data augmentation. And the idea of this TDNN is to this X-Vector system is to take a variable length audio and get a single vector representation for that entire variable length audio. So this single vector, which may be of 100 or 200, 300 dimension, should capture the speaker discrimination features actually. So this is a fixed dimensional embedding for any variable length utterance. So this is the idea of X-Vector system. There are other systems called D vector or even I vector. So those systems also get you this fixed dimensional embedding or fixed dimensional vector for a variable length utterance, but this is more robust. We'll see why it is robust compared to those. And they call this vector. So whenever they take this variable length audio, convert into vector, they call this vector as X-Vector. Right. In the same way, Google has published a paper where they do the same thing. They call it D vector. And same Johns Hopkins people, Johns Hopkins people, especially Nazim Dayak, he proposed this I vector system, and this I vector system also does the same thing. So it takes variable length utterance and creates the same fixed dimensional embedding. So they call this particular vector as X-Vector, which uses time delay neural network and some sort of statistic pooling layer to get the fixed dimension embedding for any variable length audio data. And in this paper they use data augmentation, and the data augmentation will be like something like adding noise to the data with different SNRs and adding reverberations and those sort of thing. I mean speed, you can also do speed perturbation, volume perturbation, Bayesian Gaussian noise perturbation. So a lot of things you can do, but whatever they have done is these noise and reverberation technique, and adding these sort of data augmentation will give you improvement in accuracy as well as improvement in robustness to the model. Like if your test data comes from very noisy environment and your training is only consist of very clean data, then it's a sort of mismatch. The data distributions are different, so the system performance will go down. So if you add this sort of noise to the system, the robustness will increase. Right, that's the point they are trying to prove. And also they get some improvement in performance compared to the iVector, and one more bottleneck feature based iVector system. We'll see those results in the coming slides. And what I'm going to explain in this second point is we are going to first introduce what is this acoustic iVector. Basically it's the same old iVector system. How do we use that? That's a one point. Second point, we'll see the phonetic bottleneck based iVector. That's supposed to be I here. Phonetic bottleneck iVector. And third one, we'll see the extractor system, and finally we'll see the PLDA classifier. It's not much important, but these are the main 3 points which we are going to cover in the coming slides. So coming to acoustic iVector, so the acoustic iVector is basically the same old iVector system where you have UBM. For example, here there is a UBM, and using the UBM you create speaker dependent GMMs. So this speaker dependent GMMs will give you the means of speaker if you concatenate the means of speaker dependent GMMs, then you get a super vector. So the super vector you can use the super vector is a very high dimensional vector. You can use a total variability matrix, and you can convert that you can get this I vector which actually is a small dimension, as well as it captures the speaker and channel variability, right? So that is the whole idea of I vector extraction. I mean, I'm not going to explain the full I vector extraction paper. I'm just giving you the idea like how that happens. You have UBM and you have speaker dependent GMMs. You will adopt the UBM to speaker dependent GMMs. Then you extract the super vector. As I said, you just concatenate the means. Then using total variability matrix, you get this I vector, right? And for this particular paper, they are using 20-dimensional input features as input for the UBM training. And the UBM is basically, as I said, it's also a Gaussian mixture model, but the UBM is a full covariance 2048 component full covariance. When I say 2048, is basically the, for example, if I have X and Y dimension, so these are the components, basically the M part which you see, like for example, if I write GMM, so GMM is basically sort of summation of component 1 to, let's say, component M. This M is 2048 here, and you have weighting factor CM, and every component is basically one Gaussian, right? So it will have its own mean, which can be any dimension. It depends on the feature dimension. This is 20 dimension, because in our case we are using feature dimension 20. Then it will have a covariance matrix. So covariance is 20 cross 20 matrix, right? So this is how the GMM is. So this GMM basically, I mean this probability distribution. So the GMM looks like this, and as I said, this M is basically number of component, basically number of GMMs, number of Gaussians you are using is 2048, and that and the matrix you are using is a full covariance matrix. Basically, when I say matrix, it's a usually people use only the diagonal covariance. But here they are using the full covariance just to get the entire, just to cover all, just to fill all the points, and since the data is also large, you need that. And the I vector, using I vector dimension you get after total variability matrix is I vector is at 600 dimension, as you can see here, right? So that is the idea of acoustic I vector. Coming to phonetic bottleneck I vector, this is similar to the acoustic I vector itself, but the thing is, instead of feeding only MFCC, you can also feed frame level bottleneck feature. For example, let's say you have a speech recognition system. Assume this as a speech recognition system. So this speech recognition system basically takes a sequence of frames here, takes sequence of filter bank energies, and it classifies that particular frame into one of the xenon, let's say 2000 xenons, and whenever you feed one vector here, one filter bank vector here, you get the bottleneck feature. So bottleneck feature could be any dimension. We'll see what is the dimension. So this bottleneck feature is taken and concatenated to this bottleneck feature is taken and used along with the MFCC to compute the I vector. That's the idea. So you take the bottleneck feature, then you use it with MFCC, then you do the same way how you compute the I vector, right? So then what happens is then it's similar to the acoustic I vector itself. As I said in the previous slide, acoustic I vector takes the for UBM training they take MFCC, but in our case we are taking the MFCC plus this bottleneck feature. This picture is not that completely clear. I took it from online from Google, but this picture is not completely good. But the idea is you have the MFCC, then you have the bottleneck feature for every frame. Then you just concatenate them and use it for UVM training instead of using only the 20 dimensional MFCC which you were using before, and along with 20 dimension you can use delta also, right? And coming to the final picture, which is coming to the main idea of this paper, which is the X vector system. This picture I took it from the previous paper, which is the deep neural network speaker embeddings for deep neural embeddings for speaker recognition, is the TDNN paper, as I said. So this TDNN for speaker recognition, it's a similar, something similar to any deep learning convolutional neural network or recurrent neural network, but these layers are TDNN layers, right? And if you want to understand what is TDNN, I have a tutorial which is 2015 paper for speech recognition using TDNN. You can just watch that. So basically every layer is a TDNN layer here, and these layers capture the frame level statistics or frame level features of the input audio. And once you run your frame level features, you get sequence of frame level feature. If your frame has capital T number of frames, you get T number of frame level feature. Now you somehow have to pool all those features and get a single vector, which is done by the statistics pooling layer. So the statistics pooling layer is nothing but it's an inspiration from Baumwell statistics, how people used to do Baumwell statistics in I vector extraction and other things. People also wanted to do sort of statistics here, so they use this statistic pooling, which computes the mean of the vector and standard deviation of the sequence of vector. Let's say you have sequence of frame level vectors or frame level feature, you compute the mean of this, it's a one vector, and compute standard deviation of this another vector, then you concatenate these two, right? Then when you concatenate it, this vector you can feed it to the next layer, which is this affine transformation again, and there is one more level affine transformation. This is sort of they call it segment level or sentence level utterance level feature extractors, and then at the end of this one, then you get to go to softmax layer, which basically predicts the probability of that particular speaker. Probability of the speaker for that particular utterance, right? And here is the breakdown of the system, breakdown of the network, where what is the dimension of the input, what is the dimension of the output, and as you can see, we are going to use this layer as the feature extractor or X vector. So this 512 dimension is our X vector, right? Because this is where they tap the I'm not completely sure whether it is this or this. I think it is the X vector is this, not this. So this is basically you have a pooling layer. After the pooling layer, whatever output you get from the segment 6 layers output. Yeah, basically the segment 6 layers output, this one is our feature, X vector feature, right? And thus that's same as this, because this is what is going to go as input to the segment second, right? And this is the whole thing. Like importantly, you have utterance, let's say, and this utterance will be converted into sequence of frames using MSS extractions. Then there is a frame level feature extractor which processes every frame, and once it processes every frame, you get sequence of features for every frame. Then you pool all those frames, features using statistical pooling layer. Then you apply it to two more affine transformation. Then at the end you classify that classify the speakers for that particular utterance, right? Then you compute the cross entropy, then you back propagate, and same thing repeats until you do convergence, until you reach the convergence point. Right? And PLDA classifier is nothing different. You have X vector and I vector, I vector systems. I vector they're like very high dimension 512 or 600 dimension vector, you just project them using LDA to lower dimensions, and that's what they are saying here. And these LDA dimensions, like what is the dimension should be they are projecting, they are tune it with some development data, right? And once they tune it, they say 200 dimension is good for I vector, and 150 is for good for X vector, and then they have to train the PLDA algorithm. PLDA is a backend basically. After you extract the feature, you use the PLDA to do the scores, get the scores, and these scores are normalized using S norm. Right? It's not that important, but the main idea is to the X vector idea is that particular architecture which you saw in the previous slide. Now coming to the experimentation result, we'll explain it in three different pieces. First we'll explain what is the training data, then we'll see what is the evaluation data, then we'll see how they do data augmentation. And in the training data, they are using both telephonic data, which are recorded in the telephone, and then microphone speech data, which is actually English speech data. And for training, they are using switchboard corpus, which is developed, which is collected in phase 1, 2, 3, and switchboard cellular is also present. And they're saying 28,000 recordings from 2,600 speaker, and SRE, basically the speaker recognition challenge data from NIST is also used from 2004 to 2010. And UBM is trained using both switchboard and SRE data, and PLDAs are trained only using SRE data, right? And for ASR, for the I vector bottleneck feature extraction, they have trained ASR for feature English corpus, using feature English corpus. So for evaluation, they are saying they take a speaker in the wild data set for evaluation, for testing, and they're taking NIST SRE 2016 challenge data set. And speaker in the wild basically has video, audio for English speakers, and it has a lot of noise, it seems, and it's a good idea to do data augmentation. Then for SRE's Cantonese conversation speech data, like 2016 SRE challenge data, that is for evaluation. And they're saying both enroll and test speaker in the wild utterances vary in the length between 6 to 240 seconds. And for SRE 16, the enrollment utterances contain about 60 seconds of speech, while tests are 10 to 60 seconds length. So the data augmentation, as I said, they use noise addition, adding noise to the audio and doing reverberation. The room impulse response data they use. I mean, the reverberation is basically a convolution with this room impulse response. And for adding noise, they use data from Muson, which has music, speech, and noise. And this is the statistics. It has 60 hours of speech from 12 language, and 42 hours of noise, or 42 hours of music, right? And room impulse. These two data sets are available in OpenSLR. You can just go and download if you want. Coming to the results, so there are different systems they are developed. So basically, this original system is basically, as I said, this original system has switchboard and SRE for training, and for development it's SRE 16. For PLDA training it's only SRE, right? And they have three systems, as I said: I vector acoustic, which does not use bottleneck feature, and I vector bottleneck feature based, and I vector X vector. So if you see the original system with no with the stat I said, switchboard plus SRE for X vector training and SRE for PLDA training, right? If you use that, actually the best system is this I vector bottleneck one, right? And even with EAR and DCF score, and both only for speaker in the wild, but for SRE X vector is the best, as you can see here. The PLDA augmentation is basically, they do data augmentation only for SRE data, right? Only this data augmentation. And as you can see, the system performance improves. This X vector becomes the best for this data, and best for only for ER and DCF score it is still the I vector bottleneck only, and here it's consistent, it's better for both. And coming to the extractor augmentation, the extractor augmentation is basically this one. So this UBM extractor basically, if they add augmentation to that, then they are getting 7.19 ER and DCF score of 0.53 for X vector, but still the I vector bottleneck is best here. But when you compare DCF 10 power minus 3, it is best here. The X vector is best. And the same thing if you augment both PLDA and extractors but augmentation means basically you do data augmentation here and data augmentation here, becomes the X vector becomes the state of the art in both evaluation data sets. And if you include the Voxelab data also, which is actually published by UGG group, you will reach 4.16 ER, which is like the best as of now for this. And even for the SRE Cantonese also evaluation, it's best. So the extractor, when I say it could be a UBM extractor for I vector, or it could be X vector based I vector DNN. Right? It's both. They use the both thing. And finally, this is the DET core. DET is curve basically, and detection. This when you see this curve, basically this X vector is basically the best one as of now, because if you see this is the below, this is below, and if you see the this is for Cantonese, SRE Cantonese, and even for the speaker in the wild evaluation, the DET curve is better for X vector. And that's all for this tutorial. Thank you so much for watching this tutorial. If you like the tutorial, please give a thumbs up, and if you're not subscribed to my channel, please subscribe for more video content. Thank you.